Good morning, sir. I'm Ashley Zamudio Tolenada. So today, I will discuss the proof of the theorem of cancellation and proof of the theorem of one-step subgroup test. So first, I will discuss the proof of the theorem of cancellations. This one says if you take any group, the left and the right cancellation hold. So what that means is that if I have x times y is equal to x times z, I can just cancel the x, this, on the left side and get y is equal to z. Vice versa, if I have y times x is equal to z times x, I can cancel the x on the right side and get y is equal to z. So how would you go about proving this? Well, it's not too bad. Let's just take this first equation here. So I've got x times y is equal to x times z. And what I'm gonna do is I'm just gonna take the x inverse and on the left of both sides like this. X inverse x z. Right, whatever I do one side, I have to do that in the other side also, and I have to make sure I'm doing it on the left on both sides, right? So it's not just like you're used to in algebra where everything is commutative. We don't know if everything is commutative in this case. So if I multiply by x inverse, I have to do on the left on both sides. But what happens here is I've got x times x inverse, and we know by definition x times x inverse is equal to e, the identity. And same thing on the left, right? So I've got the identity y is equal to the identity z, like that. And the identity of y is equal to, and the identity of elements times an element is just the element itself. So we got the y is equal to z. In other words, this theorem holds true, and I could do it exactly in there is in the inverse order, the exact same proof if I have this, the second one, yx is equal to zx. I'll just take an inverse on the right side like this, y times x inverse, and z times x inverse. This time and we'll get just the identity like this, y is equal to e and z is equal to e. and in the last part we got the same exact result. So this is just a quick proof that we can do and show to others the left and the right cancellations law in a group hold. And next, I'm going to prove the theorem one-step subgroup test. Let M be a group and N a non-empty subset of M. If CD inverse is in N whenever C and D are in N, and then N is a subgroup of N. We need to show that CD inverse is an element of N. So first, we will be using the associative property. Since we are assuming that N is a subset of M, therefore elements of N are in M. Associative inherited immediately. Next, and the second property, we will be using the identity property. We will let C and D is equal to X, then CD inverse is an element of N. Therefore, CD inverse is equal to X inverse is equal to identity is an element of N. And now, we're done proving the first two properties. Next, the third property, we will be using the inverse. We will let C is equal to identity and D is equal to X. Then CD inverse is equal to identity X inverse. Then is equal to, therefore, X inverse is an element of N. And the last property we will be using is closure property. We will let X inverse Y inverse is an element of H. Also, C is equal to X and D is equal to Y inverse. Then CD inverse X multiplied by Y inverse raised to -1 is equal to XY is an element of H. Therefore, inverse and closure property is satisfied. That's all. Thank you for watching.